Hello everyone, welcome to today's lecture on the I2C Communication Protocol. I2C, which stands for Inter-Integrated Circuit, is one of the most important communication protocols used in embedded systems, microcontroller based systems, biomedical instruments and IoT devices. Wherever we need a microcontroller to communicate with sensors, displays, memory devices or real-time clock modules, I2C is often the preferred communication method because it requires only two wires and supports multiple devices on the same bus. In this session, we will discuss the architecture of I2C, understand how communication takes place, learn about addressing mechanisms, acknowledgement and not acknowledgement signals, so read-write operations, and finally comparison of I2C with other popular communication protocols. So let us begin with the introduction to I2C. So I2C or I2C stands for Inter-Integrated Circuit. It was developed by Philips Semiconductor, which is now known as NXP Semiconductors, in the year 1982. The primary objective behind developing I2C was to provide a simple and efficient method for communication between integrated circuits present on the same printed circuit board. Now, what do we mean by synchronous communication? In synchronous communication, data transfer takes place with the help of a clock signal. The sender and receiver remain synchronized using this clock signal. One of the biggest advantage of I2C is that it requires only two communication lines. The first line is SDA. This line carries the actual data between devices. So second line is the SCL line. So SCL stands for serial clock line. This line carries the clock pulse generated by the master device. So because only two wires are needed, the hardware becomes simpler and less expensive. Today, I2C is widely used in sensors, EEPROM, memory devices, real-time clock modules, LCD displays, biomedical instruments, industrial automation systems and other IoT applications. Now let us understand the architecture of the I2C bus. So an I2C system consists of two types of devices, that are master devices and slave devices. The master device controls the entire communication process. Its responsibilities include generating the clock signal, initiating communication, selecting the slave device and determining whether data should be read or written. The slave device waits for commands from the master. Each slave device is assigned a unique address. Whenever the master sends a particular address, only the matching slave responds while all other devices remain inactive. So communication occurs through two common lines known as SDA and SCL. So SDA line transfer data bits. The SCL line provides clock pulses for synchronization. So one important feature of I2C is that multiple slave devices can share the same SDA and SCL lines. This significantly reduces the number of wires required in a system. For example, a microcontroller can communicate simultaneously with a temperature sensor, humidity sensor, EEPROM memory and RTC module using only two communication lines. So let us now see how the I2C protocol works internally. The SDA and SCL lines are open drain lines. This means that devices connected to these lines can pull the line low, but they cannot drive it high directly. So therefore pull-up resistors are connected. So this is the pull-up resistors, so connected to both SDA and SCL lines. So these resistors ensure that the lines remain at logic high when no device is actively pulling them low. So I2C communication operates in two modes. So the first is master mode, where the device controls communication. The second is slave mode, where the device responds to request from the master. An important rule in I2C communication is that the data line must remain stable whenever the clock line is high. So changes in data are allowed only when the clock line is low. So this rule helps prevent errors during data transfer. Communication takes place in packets. So each packet contains a start condition, slave address, read/write bit, acknowledgement bit, data bytes, and a stop condition. This organized structure ensures reliable communication between devices. Let us understand the complete sequence of data transmission. The first step is start condition. The master initiates communication by pulling the SDA line from high to low, while SCL remains high. This informs all devices that communication is about to begin. Next comes address transmission. So the master sends the address of the target slave device. Along with the address, it is also sends a read or write bit. After receiving the address, the slave checks whether the address matches its own. If the address matches, the slave sends an acknowledge signal. So this acknowledge signal tells the master that the slave is ready for communication. The next step is data transmission. So the data is transferred in 8 bytes. So after each byte, the receiver sends another acknowledgement signal to confirm successful reception. So this process continues until all data has been transferred. Finally, master generates stop condition indicating the end of the communication. So now let us understand the start and stop conditions. So it plays a critical role in I2C communication. A start condition occurs when the SDA line changes from logic high to logic low, while the SCL line remains high. Okay, so this condition alerts all devices on the bus that a new communication session is beginning. So a stop condition occurs when the SDA line changes from logic low to logic high, while the SCL lines remains high. This indicates that the communication session has ended. These two conditions act like opening and closing statements in a conversation. Without them, slave device would not know when communication begins or ends. So next, addressing mechanism. So since many devices share the same communication bus, addressing becomes essential. The most common addressing scheme is 7-bit addressing. So with 7 bits, theoretically 128 unique addresses can be generated. However, some addresses are reversed for special purposes. So the practical number is slightly lower. For applications requiring a larger number of devices, I2C also supports 10-bit addressing. In addition to the address bits, one read-write bit is transmitted. A value of 0 indicates a write operation. A value of 1 indicates the read operation. For example, if the slave address is 10100000 and the read-write bit is 0, the transmitted address byte becomes 10100000. So this tells the slave that the master wants to write data. Now let us discuss acknowledge and not acknowledge signals. ACK stands for acknowledge. It is represented by a logic 0. Okay, after receiving a byte successfully, the receiver pulls the SDA line low during the acknowledgement clock pulse. This tells the sender that communication can continue. NACK stands for not acknowledge. It is represented by a logic 1. A not acknowledge may occur when receiver is busy, when an error occurs, or when the master wants to terminate the communication. So acknowledge and not acknowledge signals improve reliability by ensuring that every transmitted byte is correctly received. So let us now study the write operation. In a write operation, the master sends information to a slave devices. The communication begins with a start condition. The master then transmits the slave address along with the write bit. The slave acknowledges the address by the sending an acknowledge signal. Next, the master sends one more data bytes. After each byte, the slave sends acknowledge. Once all data has been transmitted successfully, the master generates a stop condition. A common example is writing, configuring, setting into a sensor or storing information inside an EEPROM memory device. So in the read operation, the master receives information from a slave device. The process begins with a start condition. The master sends the slave address along with the read bit. After receiving acknowledgement from the slave begins transmitting data. The master receives the data byte and sends acknowledge signals if additional bytes are required. After receiving the final byte, the master sends a not acknowledge signal to indicate that no further data is needed. Finally, the master generates a stop condition. This operation commonly used when reading sensor measurements such as temperature, humidity, pressure or real-time clock values. Here we see the timing diagram of I2C communication. Communication begins with a start condition. So this is followed by the address field. Next comes the acknowledgement signal. So next comes the acknowledge signal. Data bytes are then transmitted sequentially. Each data byte is followed by another acknowledge signal. Finally, communication ends with a stop condition. So observe carefully, the SDA carries the data while SCL carries the clock signal. Another important observation is that data changes only when the clock is low and remains stable when the clock is high. Let us compare I2C with the SPI and UART. So I2C uses only two lines, that means two wires, and supports multiple devices through addressing. So SPI generally uses 4 wires. It provides much higher communication speed. UART also uses 2 wires but supports only point-to-point communication. I2C offers a good balance between simplicity and functionality. For application involving multiple sensors and moderate communication speed, I2 is usually the preferred choice. So let us summarize the important features of I2C. It supports multi-master communication, meaning multiple masters can exist on the same bus. It also supports multiple slave devices. Communication is address based. Both 7-bit and 10-bit address are supported. The protocol includes built-in acknowledgement mechanisms for reliability. The advantages include reduced wiring, lower cost, easy implementation, and support for multiple devices. However, compared to SPI, I2C provides lower speed and it's suitable mainly for short distance communication. So in conclusion, I2C is one of the most widely used serial communication protocol in modern embedded systems. Its two-wire architecture reduces hardware complexity while still allowing communication with multiple devices. Its reliability, simplicity and flexibility make it ideal for sensors, memory devices, displays, biomedical equipment, industrial controllers and IoT systems. Understanding I2C is essential for anyone working in embedded systems, electronics, biomedical engineering or Internet of Things applications. I hope you all understood the concept of the I2C communication protocol. Thank you for watching. Happy learning.